June 1, 1974. At 4:53 p.m., a blast carrying the force of up to 45 tons of TNT detonated across the Nypro chemical works. The explosion flattened 60 acres of infrastructure and killed 28 men, 18 crushed inside the control room when the roof collapsed. To understand how a modern facility fails this completely, we have to look at the baseline blueprint of the plant. This schematic outlines the oxidation stream, a continuous chain of 6 enormous reactors, each placed slightly lower than the last, so a highly volatile liquid called cyclohexane could flow downhill from one to the next. Inside those steel vessels, the process demanded extreme thermodynamic conditions. The cyclohexane was maintained at 155 degrees Celsius, kept liquid by 9 atmospheres of internal pressure. At room temperature, cyclohexane pours like water, but if you breach containment at that temperature, it does not leak, it flashes. The superheated liquid boils instantaneously, expanding hundreds of times its volume into a massive vapor cloud. The complex was an intricate thermodynamic trap. Safe operation relied entirely on the uninterrupted mechanical integrity of the vessels, keeping that liquid under heavy pressure. On March 27th, operators discovered a severe structural anomaly. A massive vertical stress fracture had opened in the steel shell of reactor number 5. Operating a compromised pressure vessel holding boiling, flammable liquid is impossible. Reactor 5 had to be extracted entirely, leaving a massive physical gap. This presented plant management with an expensive dilemma. They could shut the entire stream down to investigate the metallurgy and identify what was attacking the steel, or they could find a way to bridge the missing link. Because a cold plant means lost revenue, they chose to maintain the flow. They decided to connect the outlet of Reactor 4 directly to the inlet of Reactor 6, bypassing the empty space completely. Plant management officially classified this bypass as a temporary repair. That single word quietly stripped away the operational rigor normally applied to high-pressure design modifications. By prioritizing uninterrupted output over a thorough engineering investigation, the operators committed to improvising a high-pressure chemical conduit on the fly. Reactor 4 and 6 were horizontally and vertically offset, so a straight pipe couldn't bridge the gap. Lacking standard 28-inch piping, the crew improvised with a narrower 20-inch pipe. To connect them, they added 2 angled joints, creating a flattened C-shape called a dogleg. To absorb thermal movements from the massive reactors, they attached a flexible metal component called a bellows to each end of the dogleg pipe. Bellows are engineered with a strict mechanical limitation. They are designed exclusively to handle linear compression and expansion, moving straight in and out like an accordion. They possess absolutely no structural tolerance for sideways shear, bending, or twisting forces. By placing those flexible joints at the extreme ends of a multi-angled pipe, the installation forced the bellows to perform a structural stabilization role they were never designed for. When pumping superheated liquid through a bending pipe, the fluid dynamics turn hostile. 9 atmospheres of internal pressure push aggressively, attempting to force the bends open. Across this specific dogleg, that thrust generated 38 tons of continuous turning force, levering against the assembly. The only structure holding that immense load up was an improvised framework of standard scaffolding poles erected simply for workers to stand on, entirely uncalculated for 38 tons of shear weight. Subject a bellows to that kind of intense lateral pressure, and it undergoes a catastrophic mechanical failure mode known to process engineers as squirm. Squirm is the lateral buckling of the thin metal convolutions. Under sideways force, the structure folds out of linear alignment and permanently deforms. Because of the shape of the pipe, the full 38-ton turning load applied a continuous, fatal bending momentum directly onto those squirm-prone bellows. The geometry of the dogleg assembly transformed standard operating pressure into a mechanical certainty of failure. A basic stress analysis would have flagged the deadly physics of this geometry instantly. The reason it wasn't caught lies in a total organizational collapse. At the time the bypass was constructed, the plant's lead mechanical engineer had resigned. The position was vacant, leaving the site without a single qualified mechanical specialist on staff to oversee the modification. Without an engineer, there were no formal design documents. The geometry for a high-pressure pipe holding back highly explosive fluid was sketched out full-size in chalk on a workshop floor. Nobody performed the mathematical stress calculations required to identify the 38-ton turning load or to verify the load-bearing capacity of the scaffolding. This matrix shows the disparity between standard engineering protocols and what actually occurred. Protocol required a water test at 14 atmospheres. Instead, the crew executed a pneumatic nitrogen test at only 9 atmospheres. A pneumatic leak test only proves that gas isn't currently escaping the seams. It completely fails to prove the structural endurance of an assembly, subjected to continuous, heavy mechanical bending over weeks of operation. Every single procedural safeguard was bypassed. No formal drawings, no stress calculations, inadequate pressure testing, British standards ignored, manufacturer never consulted. This systemic failure turned a temporary fix into a high-pressure threat. For 2 months, the compromised metal held. Then, on the afternoon of June 1st, a slight, normally manageable fluctuation in system pressure finally pushed the weakened bellows past their physical yield point. The bellows squirmed, the convolutions buckled under the lateral shear, the dogleg jackknifes entirely out of place, and the 20-inch line tore wide open to the atmosphere. Instantaneously, 30 tons of superheated liquid cyclohexane escaped containment and flashed into a massive rolling vapor cloud, spreading rapidly across the facility. The vapor blanketed furnaces, motors, and hot surfaces. Ignition was inescapable. The detonation obliterated the control room and crushed heavy machinery like foil, taking 28 lives in a fraction of a second. This detonation resulted directly from the collision of unyielding physical laws and compromised mechanical containment. The British government convened a formal court of inquiry, chaired by Queen's Counsel Roger Parker, to investigate exactly how a major chemical complex erased itself in an afternoon. The inquiry concluded that the root cause was the normalization of deviance. The plant prioritized production continuity over baseline engineering discipline, bypassing vital safety protocols simply because it saved time. Out of the destruction at Flixborough came a sweeping regulatory legacy that birthed the modern discipline of process safety management. This incident established a new, universal industry mandate. Today, every single plant modification, regardless of scale, requires formal management of change protocols and structured hazard analysis, known as HAZOP, to interrogate every possible failure mode before construction begins. The core operational lesson is unyielding. A temporary pipe carries the exact same lethal contents at the exact same pressure as a permanent installation. Therefore, it demands the exact same engineering rigor. Flixborough stands as a permanent reminder that the most dangerous engineering decision is not the complex one. It is the quiet, reasonable-sounding choice to skip a standard safeguard simply because nothing has gone wrong yet.